let's take a look at this Gravitron problem. So we're gonna shrink our person down to a point mass, but that's okay. It'll be a rough estimate, in other words. So we have our Gravitron. It has a radius of 5 meters from the center of rotation to our person. They're on an incline of 70 degrees sitting there, and there's 0.6 meters, or 0.6 for my mu value. We want to know a couple things. We want to know if it's rotating at 24 RPM, so this is its operating speed, how many G's of radial acceleration are the occupants experiencing? And then we want to know, well, what would the minimum speed be required so that this person could then be kind of like slid up and down the wall and they wouldn't just slide down to the bottom if they like lifted up their feet. Okay. So let's get started. We're going to try and find AC to start with. So AC is equal to omega squared times R, but I need omega in the correct unit. So let's get this out of revolutions per minute and into radians per second. So we got to get rid of revolutions and go to radians. There's 2 pi radians in 1 revolution. Get rid of minutes and go to seconds. And there's 60 seconds in a minute. This comes out to 2.51-ish radians per second. Now I should be able to plug that in down here for my AC of 2.51 squared times my 5 meters. And we end up with a value of 31.6 meters per second squared. Now they asked for how many G's, so 9.8 is 1 G, so how many G's is this? So we got to go ahead and convert this as well. 9.8 meters per second squared is 1 G, and so this comes out to 3.2 G's. Meaning if you weighed 100 pounds, you would now feel like 320 pounds. That's why you can't get up and move around very easily when you're on the Gravitron, because you have such a much heavier apparent weight against the wall. Okay? All right. Part B wants to know, what is the minimum number of RPMs must it spin so that you don't slide down? Okay, so this frictional force has a kind of an interesting play here. So there is a certain number of RPMs where it could be frictionless. If it goes any slower, you'd slide down. It goes any faster, you'd slide up. That would be the situation where the coefficient of friction could be 0. But we want to know the minimum speed. So when the minimum speed occurs, that's when the frictional force is at a maximum, holding you up. If we wanted to know about the maximum number of RPMs, that would be the situation of it holding you down so you didn't slide to the top. So since it's a maximum, and this is static friction we're dealing with, it's going to be mu sub s times normal force. Remember, static friction has that range from 0 up to mu sub s times a normal force. So let's go ahead and see if we can't put this all together. So we're going to start by drawing a free body diagram. We have the force of friction on there. We also have gravity, mg, and we also have a normal force, n. So with those three, let's draw a little bit better picture here. So I have force of friction, I have normal force, and I have mg. Now, we are going to have to identify the direction of AC and make that positive. That means we're going to have force of friction and the normal force resolved into vectors. Part of it in the AC direction, part of it not in the AC direction, specifically our vertical, because we don't want them sliding up or down, so that is going to have to add up to 0. So let's get some angles figured out here. So this angle here is the same as that angle there, yeah? Those angles match. So then that makes this 70 degrees. So this here is going to be force of friction cosine of 70. This is going to be force of friction sine of 70. Now when we get over to the other side, okay, so if I was to continue this dashed line up, this would be the complement of 70, so this would be 20. That makes this the other 70 over here. So I'm going to have those two, so this is n sine 70. And this one down in here is n cosine 70. Oh my goodness, what a mess we have. Let's redraw one more time to make our lives just a little bit easier. So we have mg pointing down. I have n cosine 70 pointing up. I have n sine 70 pointing radially inward. I have force of friction cosine 70 pointing out. And I have force of friction sine 70 pointing up. All right, this is starting to look a little bit more usable. So AC is my positive direction that way. All right, now we want this to be the minimum, so we said we need this balance on that maximum force of friction. So the sum of the forces in my y direction is going to be 0, and the sum of the forces in the radial direction, so parallel to the radius, is going to equal MAC, where we're going to make a substitution here of omega squared times r, since we're looking for that omega. We will have to convert that omega into, say, revolutions per minute or something like that, but we can get there. So, force of friction, forces in the y direction. So I have force of friction sine 70 plus normal force cosine 70 minus mg equals 0. Over here we have n sine of 70 minus force of friction cosine 70 equals m omega squared times r. All right, so let's start making some substitutions. So the first substitution I'm going to want to do is I'm going to want to get rid of force of friction. Okay, so force of friction, I'm going to put in my mu times the normal force times the sine of 70 plus n cosine 70 equals mg. My next goal is I want to solve this for normal force, and then I can substitute in over there. So I have normal force is equal to mg divided by mu sine 70 plus cosine 70. Over here, we're going to make some of those same substitutions. So we're going to get n sine, let's make a dash line there, n sine 70 minus mu, static of course, n cosine 70 equals m omega squared times r. Factor out an n and substitute that in there. All right, so I have mg divided by mu sine 70 plus cosine 70 times what's left inside, which is my sine 70 minus mu cosine 70 equals m omega squared times r. My goodness, that's looking ugly, yes? So we want to get rid of the m's, that's nice. Anyone can ride the Gravitron, it's a wonderful family ride. Now we just need to solve for omega. So we're going to divide the r over, take the square root, and we will have our omega value. So this is the square root of g times the sine 70 minus mu cosine 70 divided by r times the mu sine 70 plus cosine 70 equals omega. If we plug this in, we get an omega value of 1.26 radians per second. Now before we had 2.51, so about half, maybe a little less, somewhere in there, of omega. Now if we put the g forces in here, how many g's of acceleration does it have at that point? It comes out to 0.81 g's is all that's required to get you to not slide on that wall. So they don't have to get you up to full speed before you're able to kind of stick to the wall there in the old Gravitron. There you go.